So these are two questions that were sent in the email. I'm sure everybody has the same types of questions. The question is, a certain shade of blue has a frequency of 7.03 times 10 to the 14 hertz. What is the energy of one photon? Okay. So we know from frequency, we know the relationship between frequency and energy is energy equals h mu. That's our formula. Like I said, we have two formulas for light. That's all we have to know. Okay. Energy equals h mu, and the speed of light equals wavelength times mu, times the frequency. So between those two formulas, we can calculate anything we need. And where it says hertz, hertz is Hz, hertz is the exact same thing as per second. That's what hertz means, is cycles per second. So you want to take the energy, so we're given the frequency, and we're given h. Remember, h is Planck's constant. Planck's constant is 6.626 times 10 to the minus 34 joule seconds. Our frequency is 7.03 times 10 to the 14th per second. So the seconds cancel. And you're left with joules. Joules is a measurement of energy. So all we did was use our formula and plug in the values that we know. Okay. You do the calculations, you get 6.626 times 7.03 on the calculator, and you end up with 46.58078. And then the exponents, we have 10 to the minus 34 and 10 to the 14th, which gives you 10 to the minus 20. So our answer becomes 46.58078 times 10 to the negative 20 joules. Now we convert that into sign notation, okay, and the correct number of significant figures. Okay. The measurement that we have is 7.03 times 10 to the 14 hertz. That has 3 significant digits. We're doing multiplication and division. So it's the number with the lowest number of significant digits is going to be in our answer. So our answer has to only have 3 significant digits. So it has to cut off right there. Okay. So 8 is greater than 5. So the 46.5 rounds up to 46.6. And we move the decimal point to make the number between 1 and 10. Okay. So we move the decimal point to make it 4.66. So I've made the number smaller. So I make my exponent bigger. I made my number smaller by 1. I move the decimal point 1 place. Okay. So I make the exponent bigger by 1. So it becomes 10 to the minus 19. So your answer is 4.66 times 10 to the minus 19 joules. Okay, that makes sense?
I got the numbers on the calculator just like that, so I guess.
Okay. Do you agree with my numbers? Perfect. So when you guys do it, you should get the same numbers I get. That's a great way of checking yourself, make sure you're doing it right. And a great way of checking me too, make sure I did it right. Okay. Second question on the email was the frequency of middle C note on a piano is 261.63 hertz. Again, hertz is per second. What is the wavelength of this note in centimeters? Now, you got to remember, we're dealing with sound here, not light. So instead of the speed of light equaling our wavelength times frequency, this is the speed of sound is going to equal our wavelength times our frequency. Just a little bit different constant. Okay, so the speed of sound, is going to equal our wavelength times our frequency. That's what we're dealing with here. And we want to calculate the wavelength. So you want to isolate lambda. So divide by frequency on both sides. So you get the speed of sound divided by frequency. Just rearrange this equation right here. Divided by frequency on both sides. Okay. Hilton, what's up?
What's up?
Hey, this is my grandson, by the way.
Hi.
Hello. This is when to pick up at the airport last night. He flew in from Ireland.
Oh, wow, that's far.
Yep,
Yep.
that's where at LAX.
I slept on the second flight. I slept for 7 hours.
All right. So now we got lambda, right? Everybody see we rearrange that equation. So you can see. All right. So we have lambda equals the speed of sound over mu, which is right here, of frequency. Okay. Speed of sound is 3.43.06 meters per second. Okay. Frequency is 261.63 per second. That's what hertz is. We have per seconds on the bottom, per seconds on the top. Those cancel. We're left with meters. Okay, so we do the math, it comes out to 1.3112 meters. Okay, we have 5 significant digits because our measured value has 5 significant digits. Okay, 261.63 is the measured frequency. So our answers have 5 significant digits. Okay, that's in meters. They want centimeters. Okay, so they want you to convert that into centimeters. So here's our meters, and here's our conversion. Centimeters to meters. Centi, the centi is writing 10 to the negative 2. All right, so we end up with centimeters. Our meters cancel. And when we take 10 to the negative 2 and move it up, we change the sign, right? So we have 10 to the 2. So 1.3112 times 10 to the 2 means the decimal points get moved over 2 places to the right. Okay, you're increasing it by a factor of 2. So it becomes 131.12 centimeters.
So would you be able to write that, or would it ask you to write that in scientific notation or put 131.112, because I put these numbers into the calculator and
Right.
it gave me 1.31 to 10 to the power of 2.
Same thing, same answer. If they want a sign notation, you put in sign notation.
Okay, and it won't dock you for the test like it does on the homework and stuff?
Well, if I want a sign notation, it will ask you sign notation.
Okay, okay,
Yep, but other than that, they're both exact same number.
okay.
Okay. So any questions on those two? We understand it? Perfect. All right. So that was questions from chapter 4, last time I went over. If there's any pertinent questions, I can answer those now, or we can start on chapter 5 and then review any questions you have at the end. But any burning questions, let me know now. We can go through that. Did you want to go through that the SPDF orbitals again, real quick before we start that?
You mean the electron configuration?
Electron configurations.
Yeah.
Yeah. Okay. Okay. So here's our periodic table. When we divide this up, we just color code it. Remember this helium we put right over here. Helium and hydrogen are together. So this 2 columns is our S's. Okay. This 6 columns right here is our P's. This middle section is our D's. And this section on the bottom here, this is our F's. And S's always start with 1. P's start with 2. D's start with 3. And F's start with 4. So whenever we have an element, we can just count the periodic table and just go through each of those sections. Now, when we do that, okay, we end each section where it ends at the markings on the periodic table. Okay, So with the helium, with the S's, we're going to end with S2 because here's 1 and 2. Okay. For the P's, you have 1, 2, 3, 4, 5, 6. So you can always end with SP6 for the completed section. The D's, we go to 10. We're going to always end with that. F's to go to 14. Okay, that's just the number of columns that we have. And all you're going to do is count where your unit is. So let's pick an element. Let's pick this one right here, rubidium. All right. So rubidium is going to start at the top, and every time we complete a section, whether it's going to be S, P, D, or F, we're going to write that down. So the first section, this is our energy level here. This is number 1. So it's 1 S2 because we've gone 2 sections now. That gave us to helium. Then from helium, we go to lithium. Okay. Then we got 2 S2 as we move across. That gave us 2 beryllium to right here. Okay. We go keep going across. Just keep working our way straight across. Okay. And again, the P start with 2. So 2P, and we go all across that. There's 6 of them, all the way to neon. Okay. You go down to the next level. Next level is a 3. And it's still in our S's. Those are our S columns right there. So we have 3 S2. We go straight across again. Okay. And that's the third column. That's 3, because the column above it was 2s. Next column is 3s. So 3P6. And that got us all the way to argon. Okay, we're running out of room here. We drop down the next column, which is 4. So 4S2, let's put it right. This is pretend it's a continuation, 4S2. And now for here, that got us to calcium. Okay, so whoops. Where was I at? There we go. That got us to calcium. Okay, so now we start with the D's, and our D's start with 3. So 3D10. We go all the way across to zinc. And then we start with the P's again. Now this was 2, 3, and this is 4P. 4P6 goes right across to krypton. Then go down to 5. So 5S2. Okay, that brings us right to strontium. And then we have 4D. Remember the D started with 3. This was the 3 columns for the D's. This is the 4. So D1, 2, 3, 4, 5, 6. 4D6. That's the electrode configuration. It's 1S2, 2S2, 2P6, 3S2, 3P6, 4S2, 3D10, 4P6, 5S2, 4D6. So this number here, this energy that we're seeing, this number here, this gives you the number of the S and P orbitals in that row. Okay. That number there, always it starts with your S and P orbitals. Your D is going to be 1 less because D start with 3. Okay. But the energy level on the left-hand side is always going to match your S and P orbitals. Okay. The only one that's different is the D, it's going to be 1 less because of where it starts. Did that make a little more sense this time?
Yeah, it does.
Okay, good, good. All right, any other questions on that one? It helps with the periodic table being up on the screen. All right. So let's start on chapter 5. Put a blank screen here. Bring that book up. Chapter 5 is going to be on naming ionic and covalent compounds and how they determined by Lewis electrons. Okay, so it starts off in chapter 5 with Lewis symbols and the octet rule. We talked a little bit of the octet rule last time. The octet rule means everything wants to have 8 electrons, whether they lose electrons to get there or gain electrons. If the element is to the right side of carbon, again, come back to our periodic table. Here's carbon, this is our neutral point right here. Elements to this side are going to lose electrons. This will lose 1, this will lose 2, this will lose 3 to give you a positive charge. Carbons are neutron, that gives you 8 valence electrons to the inner core. And going this way from carbon, this is going to be -3, -2, -1. They're going to gain electrons. Remember, electrons are a negative charge. So if you gain an electron, you're increasing your negativity, the amount of negative charge. So this first column is always +1. Second column here is always +2. Third column here is always +3. Then your neutral column. Then this column here is -3, -2, -1. And noble gases are always 0 because they have 8 valence electrons. Their valence shell is filled. They want to have 8, they're stable, so they don't want to react with anything else to lose or gain an electron. Okay? That's basically the octet rule. Okay? And that's how the columns work with it. So if we were to have the orbitals, remember this is your S1 orbital, this is your S2 orbital. Okay? These are the energy levels that they're going to assign with it depending where they're at. This is your P1, this is your S2P1, S2P3, S2P4, P5, and P6. So again, S2P6 would be this last one here. P5. P6 gives you the noble gas. This is your S2P5 column right there, because it wants 1 electron. Your noble gases were S2P6, with the number being on the left of the energy level. That fills your octet. Okay. So if you wanted to draw a Lewis structure or Lewis symbol, okay, you would draw the number of valence electrons from this periodic table. So if I wanted to draw, let's get this cleared off so you can see a little bit better. If I wanted to draw the Lewis representation, the Lewis, what's it called? Lewis symbol for, say, magnesium. You would draw magnesium. And how many valence electrons does magnesium have? Remember, this column has 2 valence electrons. So you would draw 2 dots. Right? To become stable, magnesium is going to lose those 2 valence electrons to give you Mg2+. Everybody see why it's a positive, why it's +2 when you're losing electrons. Okay. If we look at magnesium, it's got 12 protons in the center. So we're going to go back to a so magnesium has 12 protons in the center. So this is magnesium. It's got 12 protons in the center, 12 plus charges. And it's got 12 electrons flying around it. That's your S orbital. This is your P orbital. It has 2. This has 8. And then your outer shell here has 2 electrons in the outer shell. If you lose those 2 electrons, you now have 10 electrons. So you got 10 negative charges, 12 positive charges. That ends up as +2. Okay, that's how you get a sign. So your valence electrons are the outer electrons. You're either going to lose electrons from the outer shell or gain electrons in that outer shell. Like you go to fluorine. Fluorine is right here on the periodic table. Okay, that's clear. Okay. Fluorine has 7 valence electrons, right? Because this, remember, our periodic table has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Those are your outer electrons. Like we said, 4 is the midpoint. It's lower than 4, then they tend to lose the electrons and become positive. If it's greater than 4, it's easier to pull electrons in. And if you got 5 electrons to get to 8, it's easier to gain 3 than it is to lose 5. So those gain electrons. Okay? You want to end up with an inner core of 8. Your outer shell to have 8. That's where elements are stable. So fluorine has 7. So again, if we have fluorine, we have 7 valence electrons. So fluorine representation is 1, 2, 3, 4, 5, 6, 7. And again, we can gain electron right here to make it F minus. That gives you 1 extra electron. But that's how you write the Lewis dot structure or Lewis symbol. So oxygen, how would you write the Lewis symbol? Look at oxygen periodic table. Look at what I just told you. How many valence electrons does oxygen have? Somebody should be able to count it. How many valence electrons?
2.
Go back to our table here. Okay. This whole column has 1. This column has 2, 3, 4, 5, 6, 7,
6.
and then 8. So how many electrons how many valence electrons does oxygen have?
6.
6. Perfect. That's 6. So we make 6 dots. So 1, 2, 3, 4. You spread them around. Okay, and then pair up 2 of them. And that gives you 6. You cannot put it like this. This would be wrong. 1, 2, 3, 4, 5, 6. You got to spread them out evenly as you can. And you can't leave one side blank. Okay, so oxygen has 6. Look at, and you put 6 dots. So let's look at, let's see, how about carbon? Look at carbon on the periodic table. How many valence electrons, how many dots would you put around carbon?
Four?
Carbon. Perfect. Exactly. 4. Carbon has 4 valence electrons. Which way would you write it? Would you write it like this? 1, 2, 3, 4. Or would you write it 1, 2, 3, 4? Top or bottom? Which one's correct?
Bottom.
Bottom.
Bottom one. Perfect. Because you got to spread them out. And those are Lewis dot structures. That's it. Those are your Lewis representations. From there, we'll draw Lewis structures. But this is the basis that we need. All right. Let's do one more. Let's do, how about nitrogen? Someone tell me how many nitrogen, how many valence electrons nitrogen has, then we'll go on.
5.
5. Perfect. So you write 1, 2, 3, 4, and you pair one up. 5. Okay. So that's why nitrogen is going to accept 3 electrons. 1 there, 1 there, and 1 there to give you 8. That's why nitrogen is N3 minus as an ion. And that's how it's going to combine. We're going to use that when we combine these ions. Okay, so ions with positive and negative charges. Okay. Again, the ion it's built to fulfill the energy shell to have 8. That's where it's most stable. That's where the first column is +1, next column is +2, +3. Carbon's neutral, and then nitrogen is -3, oxygen is -2, fluorine is -1, and then the noble gases. Okay, that's how your ions are work. Now the ones in the center. Okay, these right here. Can't get rid of some of those marks already. Okay, but this center group right here. These are called transitional metals. Remember, everything, this line right here that goes through the periodic table, everything to the left is metals, everything to the right is non-metals. We're gonna have to know that we can compare those two. So these are your transitional metals. Transitional, meaning they don't have a charge we can assign to them. They vary. Like copper can be +2 or +3. Nickel can be +1 or +2. Copper can be +2 or +3. Okay. Titanium can be +4 or +6. Okay. Zinc can be +1 or +2. So we don't know the charge on those. Those can vary because how they spread out their energy levels in the energy fields of electrons. So those can vary. Those are your transitional metals. Okay. So atoms with positive charges, atoms with negative charges. When we're dealing with transitional metals, we put the charge, when we're writing the name, in parentheses and then the Roman numeral for that charge. So if we had like copper oxide, we put copper and then you put the charge, whether it's 1 or 2. We put a Roman numeral 1 and then you put oxygen. You have to include this Roman numeral so we know what charge it is because it can vary. If it's one of the other metals, one of the elements, we don't need the charge because it can only be 1. It can only be 1, +1, +2 set in those columns. If it's transitional, we have to include the charge when we name it so we know what it is. Okay. Iron, Fe. Fe can be +2, which is iron 2, or it could be iron 3. That's not very good. 3. Okay. You put Roman numerals following the element. All right, let me get that in case I need a periodic table again. Get some of this off of here. Keep it kind of clear. All right, perfect. So that leads us to naming these cations. When you name a cation is a positive charge, and anion is a negative charge. When you're naming chemical compounds, the cation keeps its name. So if you want to name Na+, that's sodium. Ca2+ is calcium. Okay. So when you have a cation, you just name that as it is on the periodic table. Makes it simple. Okay. If you have Fe2+, that's iron 2. Okay. It's just the name you give it on the periodic table. Now, when you have a anion, you change the name. Okay. Okay. On the periodic tables, S is sulfur, right? You drop the ending and add IDE when it's an ion. So that becomes sulfide. Chlorine, Cl, becomes chloride. Okay, so when you have an anion, you drop the ending, the ending, and add IDE to the end. Okay, so oxygen. Okay, oxygen is O, that's oxygen. When it becomes an ion, O2-, it becomes oxide, IDE. Okay. So the cations keep their names, the anions drop the ending and add IDE. So your positive charges are the name of the periodic table. The negative charges are the names with the ending changed to IDE. Okay, so that's how we name things. We always name the cation first. So table salt. Table salt is NaCl. Okay. And it's sodium chloride, not sodium chlorine, because the anion changed the IDE ending. Because as we're going to see, they combine in a 1-to-1 ratio. Because Na is +1, chlorine is -1. So when they combine, the cation and the anion combine in a 1-to-1 ratio, it's plus and minus, because it has to be neutral. Your balance has to be neutral. It becomes sodium chloride. Okay. So that's naming our cations. And then we get into polyatomic ions. We can name and predict the charges. We know how to predict the charges from the periodic table. You know what's +1, what's +2, what's +3, what's -3, -2, and -1 by looking at where they are in the column of the periodic table. You know how to do that. We went through each column and said what the charge is going to be. So now you know the charges and how to combine them. Okay? What's up, bud?
What's up?
You watching class again? All right, so let's do a couple examples and show you how we combine these. These are what's called ionic compounds. Ionic compounds means you're combining a metal and a non-metal. Remember your periodic table. This line, not really, that's not right here, this line that goes through here. Everything to the left of that blue line that I drew is a metal, which means it will have a positive charge. It's a cation. Everything to the right of that line is a non-metal, which means it will have a negative charge. Okay. When
Doctor,
two-
can I interrupt you? I'm sorry. There's an ionic compound table on your data packet if anybody wanted to bring that up.
Okay, like the polyatomic ion one?
The ionic compound, transitional or varying charge, and it's all outlined like you have it here.
Okay, perfect, perfect. All right, thank you. Yeah, I got some more examples from that data packet too. It's really helpful. That's great. So when you're combining a metal and a non-metal, that's what's called an ionic compound. Okay, then we have a plus and a minus, and they combine strictly by charge. Okay, when two non-metals combine, that's called covalent. Okay, so when a metal and a non-metal combine, it's ionic. When two non-metals combine, that's covalent. The metals don't combine with each other. They don't form bonds. So you either got a metal and a non-metal, or you got two non-metals. And they're going to combine differently. We're going to name them differently because there's different properties. We're going to deal with ionic compounds first. Ionic compounds have a charge, and that charge has to balance. Okay, so there's your ionic and covalent, and there's your dividing line. So let's leave that. So let's go down back here. So let's combine, let's look at the periodic table, and let's combine, let me pull some up here so I can see too while we're working. Let's combine calcium and oxygen. All right. Now that's a metal and a non-metal. Calcium is to the left of that thick line, oxygen to the right of that thick line. Okay. So they're combined by charge. Look at the periodic table. Everybody should have periodic table up. What's the charge on calcium? You should all be able to tell me that by now. What's the charge on the ion for calcium? What column is it in?
2.
Perfect. And it's going to be what? Negative or positive?
Positive.
Positive. Everything to the left of the line is positive. All metals are positive. Okay, now look at oxygen. Look where it is in the periodic table. What's the charge associated with oxygen?
6.
No, it's the valence electrons. What's the charge? Remember, the charges go 1, 2, 3, -3, -2, -1. The carbon in the center.
-2.
-2, perfect. So calcium and oxygen combine 1 to 1. Calcium is +2, oxygen is -2. So CaO is how it combines. When they combine, when there's a number 1 there, we don't put that, we don't write that in our formula. Okay? We just leave it as that. When there's nothing, there's no subscript. Nothing, we don't put 1 here and a 1 here. If there's nothing there, we assume it's a 1. We know it's a 1. So calcium is +2 minus oxygen. They combine, that's a neutral compound now. So this is called calcium oxide. IDE ending for the anion, for the negative charge. Okay. Let's combine. Let's combine boron. Boron's number 5. All right, let's use aluminum. Let's combine aluminum and phosphorus. What's the charge on aluminum? Look where it is in the periodic table. What's that charge in that column?
+3.
+3. And look at phosphorus. Find P, number 15. What's the charge on that column?
-3.
-3. Perfect. You got this down pat now. So you're combining a metal and a non-metal. So it's ionic. So it combines by charge. So it's a 1-to-1 charge. So it's AlP. And that is aluminum. And this is phosphorus. So it's phosphide, ID ending. The OS gets dropped and it becomes phos. There's an S in there. Phosphide. Okay. So aluminum phosphide is AlP. As long as it's a combination of a metal and a non-metal, we know the charge they're going to balance. Now let's do different charges. Okay, that should be making sense now. Let's do magnesium and chlorine. What's the charge on magnesium? Magnesium is number 12. What's the charge on it?
+2.
+2.
+2. What's the charge on chlorine?
-1.
-1. Okay, charges don't balance. Now we have to balance them. So if I have 1 magnesium, how many chlorine do I need to balance that? Each chlorine is -1. I gotta make the chlorines -2 also, right? So I need 2 chlorines. So the formula is MgCl2. The charges have to balance. Magnesium has 2 plus charges. Chlorine has a -1 charge. So I need 2 of those to give me a +2 on this side and a -2 on that side. They have to balance. They have to be neutral. Okay. So this becomes magnesium. Again, the metal just gets its name right from the periodic table. And then chlorine becomes chloride. The anion always changes the name to IDE. The cation is always first, the non-metal or the anion is always second. So magnesium chloride is MgCl2. Okay. There's an easy rule, little trick, shortcut we want, that makes it very simple to do. It's called the crisscross method. Okay, we have magnesium chloride right here. So we write MgCl and we crisscross. The 2 is over here. We put that here. The 1's right here. We put that there. So we get rid of the 1 because that's never written, and MgCl2. We just crisscross the numbers. And it's not important for this. Like, well, let's do like aluminum oxide, aluminum oxygen. Now, what's the charge on aluminum? We should all be getting this real quick now. What's aluminum? Just write the charge on your periodic table above each column. That way you won't ever forget them. So what's the charge on aluminum?
Positive?
+3.
3
+3.
positive, right?
Yeah.
It's in the 3 plus column. What's the charge on oxygen?
2 negative or -2?
Perfect, 2 negative. Okay, now how do you balance that? You can multiply each by 2, multiply aluminum by 2 and the oxygen by 3 to give you a value of 6 to make it even, but just crisscross it. Take this number here and move it to the aluminum, this number here and move to the oxygen. You come out with Al2O3. Crisscross the numbers. Aluminum is +3, 2 times is +6. Oxygen is -2, 3 times it's -6. It balances. So just put the little numbers above it and crisscross them. Okay? Just be careful that you do the lowest numbers possible. You can run into trouble, like I said, you don't put the 1s. Make sure you don't put the 1s. And if you come out with, I'm trying to think of something that would work. Opposite, like if we had let's do calcium and sulfur. Okay, calcium is +2, sulfur is 2 minus. Okay, crisscross, you get Ca2S2. You can't have 2 and 2; those reduce to 1 and 1. So So it's just CAS. So just don't get caught with that. That's one little exception you got to watch out for when you crisscross them. If they're the same number, just reduce them to 1, because it's a 1-to-1 ratio. And that's called calcium sulfide. So these are your ionic compounds. Okay. These are combinations of a metal and a non-metal. So when we name this thing, you'll have to name it for the midterm. This is named aluminum oxide. It is not. You don't name the subscripts. See this little 2 down here? And this little 3 down here? This is not dialuminum trioxide. When we do covalent compounds, we do name the subscripts because there's no charges. They're both negative. There's nothing to balance. So we have to tell which combination it is. So if it's an ionic compound, you never name those subscripts. You just name the 2 elements involved because they can only balance one possible way, by charge. When it's covalent, you have to name the subscripts. Okay, so let's do a couple covalent ones. Covalent means 2 nonmetals. So let's combine. Sulfur, SO2. Okay, look at sulfur on the periodic table and look at oxygen. You can see they're both nonmetals, which means the ionic rules do not apply. Now it's different rules. These are covalent compounds because they're 2 nonmetals. But again, you name the first one just like it is in the periodic table. So this is sulfur. Okay. Now the second one is oxide. There's 2 of them. So it becomes dioxide. So sulfur dioxide. You name the subscript. Now if you have SO, now you do name this, if it's the first one here, if it's a 1, you never name it. If it's the second one, then you do name it as 1. So this would be sulfur, okay, monoxide or monoxide. You drop the O's with 2 O's together. Okay. So you name the subscripts. If it's a 1 for the first one, you never name it. If it's a 1 for the second one, then you do name it as a mono. Mono means 1. So it's mono, di, tri, tetra. There's a whole list. I think I put them on your table here. Oh, I didn't put them on. I didn't copy them over, did I? No. Okay, but it's mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca, or how you would name it. And then they're on your data packet. So let's combine some more. Let's combine. Okay, again, phosphorus and chlorine. You have to look at your periodic table. You have to learn how to use the periodic table. Notice they're both on the non-metal side. So you have to name the subscripts. 8 is octa. So it's octa phosphorus. Again, the first one is named just like periodic table name. And then that's 8. Octa is 8. And then tri is 3. And this is the last one. So it's IDE ending. So that P8CO3 is octa phosphorus trichloride. Okay. So 2 different naming systems. Okay. Now the only kind of hitch in that is our transitional metals in naming it. You have to remember to use, like I said, that Roman numeral. So if you're given a compound like Fe, Cl3, okay, you know that is an ionic compound, so you do not name the subscripts. But you also have to realize that Fe is a transitional metal, which means you do not know the charge. You have to determine it from the formula. So chlorine, you know, is what's the charge on chlorine ion? Find chlorine ion periodic
Negative
table.
one.
-1, perfect. So chlorine is -1. So how many chlorines are there? How many chlorine atoms are in the formula?
3.
3. Chlorine 3 times. So this whole side has a -3 charge, right? 3 -1 charges. So that means this side has to have 3 positive charges. So if you have to write this up, this is going to be iron 3 chloride.
I'm sorry, where'd you get the -1 charge?
On periodic table, look at chlorine in the periodic table.
Okay,
Look at the column. That whole column is -1, right?
yeah,
Remember this. Remember, it's an ionic compound. It's a metal and a non-metal. So you go by charges. So that whole column is -1.
oh, okay,
Okay.
got it.
So there's 3 of them. So you have to put this in the name or it will be wrong. Because there's no other way to know it once you write it out. Okay, so that's the one that you have to remember. If you're doing the ionic compound and you notice there is a transitional metal, then you have to write the Roman numeral. Okay, let's write MnO4. Okay, again, look at Mn, number 25, manganese. You know it's a transitional metal. So divide this in half. What's the charge on oxygen?
-2.
-2. Perfect. And how many do we have?
4.
4. So what's the total negative charges? We have 4 -2 charges. So we have a total of
6.
-8, right?
Oh.
So this has to have a positive on this side. So the name has to be manganese. And the charge has to be 8, 5. And then oxide. Manganese, 8, oxide. You have to make sure so once you see it's a transitional metal, you just have to remember to put that Roman numeral.
How did you get 8 out of 4 and 2 negative charges?
If I have 4 -2 charges, right? Add those together.
Oh, I see. Okay, because you
Yeah, 4
multiplied it. I thought that
times
you just
-2.
literally- Yeah, because I thought you added -4 plus -2.
Nope, 4 -2
So it'd
charges.
be- Okay, that makes sense now.
Does that make sense now?
Yeah.
Perfect. Okay. And sometimes you gotta be a little careful how you do them. Like, let's name that one. You know it's gonna be iron, right? And you know it's gonna be oxide. Okay. But you know this is a transitional metal. So here, we'll draw our line. And what's the charge on oxygen? We just said it was -2. And we got 3 of them. So what's the total negative charge on that side?
6.
-6. So this side, other side has to be +6. But be really careful because iron, we have 2 of them. So the charge if there's 2 irons, each one has to be what charge to make it a total of +6. Okay. If iron was +6, it would be 12. So what does the iron have to be?
12.
Not 12. Iron has to be 3. Because 3 If it's +3 two times, that's your +6. So you have to watch these numbers and think it through. Okay? You have to have a total of +6. If each one's +3, it's going to be a total of +6. If each one was +6, that'd be 12. Or if each was +2, it'd be 4. Okay? You got to make sure your charge is balanced. And you think about how many you have on each side. We have 2 irons, and the total charge has to be +6. So each one has to be +3. Okay? So don't just automatically assign it. Something you got to think it through. Okay? But it's just keep the math simple. Think logically through it. Okay? So that's how you name ionic compounds, transitional metals, and covalent compounds. Now, just in case I wasn't confusing enough, we've got what's called polyatomic ions, which are covalent compounds that have a charge. So these are ions. And I put a list here. This is in your data packet. These are the most common ones right here. There's only one positive one. All the rest are negative. NH4 plus is ammonium. Okay? So we can use NH4 with a positive charge and combine with anything else. Nitrate is NO3 minus. Again, these are covalent compounds like nitrogen and oxygen, sulfur and oxygen. Those are all nonmetals, but they combine in such a way to have a charge. That makes them polyatomic ions. They're ions, and they're more than one atom, polyatomic. That's where the name comes from. And all you have to do is memorize all of these. I'm just kidding. Don't memorize all of these, okay? Do not memorize it. You will have you learn to understand this table. Keep it, just understand the table, and you have it right in front of you. You want to have phosphate, it's PO4, 3 minus. Cyanide is CN minus. Hydroxide is OH minus. We treat it just the same as we would any other negative or positive charge. We balance it. Okay, so if we had a compound, let's pick carbonate. Carbonate is CO3 2 minus. So let's go back down here. Remember, carbonate is CO3 2 minus. I saw a blank slide there. All right, oops. Okay, so we know carbonate from our chart is CO3 2 minus. Okay, if we had, so let's combine sodium carbonate. We have sodium and we have carbonate. The charge on carbonate is 2 minus. What's the charge on sodium? Look at your periodic table. Sodium is number 11. So what's the charge?
+1.
+1, perfect. Okay, crisscross. Put the 2 here, put the 1 here. So put the 2 with the sodium and CO3. That's sodium carbonate, Na2CO3, because sodium is +1 and there's 2 of them. So on this side, there's +2. And CO3 is a polyatomic ion that has a -2 charge, and that balances. Okay? Again, never name the subscripts. This is not disodium carbonate. I guarantee you 30% of the class is going to miss this on the midterm. Because one of the choices of your multiple choice exam is going to be disodium carbon trioxide to name this thing. That is not disodium carbon trioxide. That is sodium carbonate. Okay. Know your polyatomic ions. Okay. Know how to name them. Now, if you have to make it more than one as a polyatomic ion, you have to use parentheses. Let's say we have aluminum carbonate. So we combine aluminum and we're going to combine carbonate. Okay. What's the charge on aluminum? Look in your periodic table. We should be getting these really quick now.
+3.
+3, perfect. You got this down pat, good. And
Yeah, finally I
carbonate-
got something down good.
I know, there you go.
Yesterday I was struggling with the other thing, and now today I'm actually acing something. So I'm
Good.
happy about
It's
that.
like that. Just certain things can be hard for certain people, and it just takes practice doing it. But if you work at it, you will get them. And CO3 has a 2 minus charge, we said, carbonate. So we crisscross. We put the 2 with the aluminum and the 3 with the carbonate. So we come up with aluminum, Al2, and then CO3. Since this is a polyatomic ion, we have to group it and say there's 3 of these groups. Okay. So it gives you 2 aluminums. Each one's a +3. That gives you +6. We have 3 carbonates. Each carbonate's -2. That gives you -6. Okay, and you just name it with the name of the first one and then the name of the polyatomic ion. Now there's only one positive one, and that's ammonium. Ammonium's NH4 plus. So if I told you to write ammonium, let's do oxide. Okay. Ammonium, you know, is polyatomic ion. Just look on the chart, see the word ammonium. Ammonium's NH4. Oxide is oxygen. Okay, ID, NE for oxygen. The charge on ammonium, we said, was +1. The charge on oxygen is what?
-2.
-2. Perfect. Crisscross them. So NH4 gets the 2. Oxygen gets the 1. So NH4, 2, oxygen. Okay. Again, it's an ionic compound, just has a polyatomic ion. Do not ever name this subscript. You only name the subscript if it is a covalent compound. So do not, I mean, I'll put on the exam ammonium oxide, and I'll put diammonium oxide. Do not pick diammonium oxide. You never name the substrate if it's ionic. And remember, ionic compound is a metal and a non-metal, or a polyatomic ion and another element. Because there is one positive polyatomic ion. Okay, let's do one more. Let's do, I think of a good one here. Let's do potassium. Potassium hydroxide. Okay, potassium is K. Hydroxide, again, look here. If that is not on the periodic table, find hydroxide periodic table. It's not there, right? So looking at polyatomic ion chart, hydroxide is OH, and it's a -1, and potassium has, what's the charge on K? It's number 19.
It's +1.
+1, perfect. So KOH, potassium hydroxide. Okay. Do not circle potassium, oxygen, hydride, or potassium, oxygen, hydrogen. Those are not names, that's just listing the elements. Okay. The name is potassium hydroxide. Kind of know your periodic table when you're looking at it, so you can realize it when you see these compounds. Okay. So that's how everything works. Let's do a couple examples, and let's see. Name that compound for me. I'll give you a hint. If you see more than 3 elements, look in the polyatomic ion chart. Because everything we're naming is binary by 2. It's 2 things combined. All right, who wants to take a shot at that name? First of all, what's the first part of the name? That should be straightforward.
Sodium.
Perfect, sodium. First part is sodium.
Is it is it sodium sulfate?
You got it. That's perfect. Perfect.
I was looking at but see, I'm confused because I was looking at the polyionic ions. And
Right?
it says SO4 and then an exponent of -2.
Right. Which is exactly right. Because that means this thing here has a 2- charge. That
Okay.
means sodium is +1. So I have to have 2 of those to balance it, to give it a +2 charge. Because each sodium is 1. We use the charge to balance the number of ions, number of elements that combine to it. So you're absolutely right. Sodium sulfate. That makes sense?
Kind of.
Okay.
It's because I'm trying to follow along. I haven't really been into chapter 5, so I'm trying to follow
Okay.
along with you as you go.
That's okay. You're doing good.
Together.
Let's name this one. It's not Alpo.
Aluminum phosphate?
That's it. You got it. Perfect. Aluminum. Phosphate. Phosphate has a -3 charge. Aluminum has a +1 charge. So it takes 3 of them to match with the phosphate. So you should be able to go either way now. Okay. Name this compound. Ni. No takers on this one?
Is the last part chloride?
Yep, it sure is. What's the first part?
Um,
Ni-
nitrogen,
Ni's number 28.
number 28 is nickel chloride.
Perfect.
Right?
Well, not per yet. Nickel chloride. Now, someone tell me what's wrong. Someone say that's not right. We're missing something. What are we missing?
The Roman numeral?
Perfect. Perfect. The Roman numerals. Nickel is a transitional metal.
Oh,
You
yeah.
you have to determine its charge. Chlorine is -1, and there's 2 of them. So you have a total of -2. So this side has to be a total of +2. So that's going to be nickel 2 chloride. Make sense? So far, so good. We've got naming ionic compounds, writing formulas, we did that. Writing formulas for ionic compounds. Covalent bonds. So basically, we're looking at things. We talked about ionic compounds, which are metal and a non-metal, and covalent compounds, which are 2 non-metals. So ionic compounds transfer electrons and create a charge. The electron actually moves from one to the other. The positive side gives up electrons. The negative sides accept electrons. Okay? So there's a transferring of electrons. That's what gives you that. That's what holds it together, the plus and minus charges. Covalent compounds share electrons. Okay? So let's take fluorine for an example. Now, what we need to realize is a chemical bond is 2 electrons. 2 electrons make up a chemical bond. So whether they're shared or transferred is what determines whether they're ionic or covalent. So let's take fluorine. Fluorine has how many valence electrons? Not the charge now. How many valence electrons does fluorine have on it? Remember, we put the numbers across. So fluorine would have how many valence electrons? Pardon?
7.
7. Perfect. You got it. So 1, 2, 3, 4, 5, 6, 7, right? So fluorine, another fluorine has 1, 2, 3, 4, 5, 6, 7. These 2 electrons between them form a bond. So we get fluorine, we draw a line. This line represents a bond. And that's how we have a covalent bond. We share the electrons between them. Okay. Hydrofluoric acid. Let's go HF. Okay. Fluorine has 7. 7. Hydrogen, let's do hydrogen different color, has 1. Okay. We've got 8 around fluorine and 2 around the hydrogen because it's being shared there. Hydrogen is our exception to the octet rule. Hydrogen doesn't have the p orbital in its row. So it can only have 2 electrons to be stable, like helium. So hydrogen follows what's called the duet rule. Everything else follows the octet rule. So hydrogen has 2 electrons around it here, these 2 shared, and fluorine has 8. So it's hydrogen fluoride or hydrofluoric acid. Okay, those are covalent compounds. They're sharing a bond between them. Okay. And that's, we can draw what's called Lewis structures for these compounds. Then we draw Lewis structures. Let's draw the Lewis structure for water, H2O. All right, to draw Lewis structures, we have to count for all the valence electrons. Remember, everything has to have 8 except hydrogen has to have 2. And when you get to realize hydrogen, once we fill the 2 around hydrogen, it stops. So there's certain things that end. We can't put them in the middle, like hydrogen and the halogens, because those will have their orbits filled with 1 electron. So then they stop. And I'll show you a couple examples of that. So the first thing we do in doing Lewis structures is count your valence electrons. So we have 2 hydrogens and we have 1 oxygen. How many valence electrons does hydrogen have? Remember, we perfect, 1. And there's, so 2 times 1 is 2. Oxygen is 1 times, how many valence electrons does oxygen have?
6.
6. Total, 6 times 1 is not 2. 6 times 1 is 6. 6 and 2, add those together, we get 8. So our Lewis structure has to have 8 valence electrons. Okay, that's what it has to have. So we take the hydrogen can't be in the center because they end, because they only have 2 electrons. So we put oxygen in the center. Oxygen has 1, 2, 3, 4, 5, 6 valence electrons. Hydrogen has 1. Put 1 there, put 1 there. Okay, that gives you a total of 8 valence electrons around hydrogen, around oxygen, and 2 around hydrogen. Okay, so we drew our structure. So we have H2O. Okay, when we have 2 electrons shared between atoms, we make a bond. Every single bond, every line is 2 electrons. So in this structure, count our valence electrons. If we start right here, we've got 2, 3, 4, 5, 6, 7, we have 8. 8 valence electrons, 8 valence electrons. That's our Lewis structure. Okay. We have to have the same number of valence electrons we have to count for. Okay, it's not all this simple. Okay, but that's how we do any Lewis structures. Let's do ammonia. Ammonia is NH3. Okay. How many valence electrons does nitrogen have? Look what column it's in. How many valence electrons?
5.
5. And hydrogen has 1. And there's 3 of those. So we got to have 8, again, 8 valence electrons. So nitrogen goes in the center. And we put in 5 valence electrons. There's nitrogen. Then we're going to add 3 hydrogens to it. Put a hydrogen here, and a hydrogen here. So we end up with nitrogen with 2 electrons out there that aren't in any bond, and our 3 hydrogens. So count your valence electrons. Every line has 2. So 2, 4, 6, and then there's 2 dots on top. Okay, those free electrons are important because they're going to determine the shape of the molecules. And shape is extremely important how things work. All drugs, organic compounds, all work by shape in your body. They all respond to different shape receptors. So that's the Lewis structure for ammonia. Okay, again, 8. You had 8 to start with, and you have 8 when we finished. Now, these are single bonds. There's other ways to do this. Let's give a little bit tougher example. Let's do carbon dioxide. Okay. We put, how many valence electrons does carbon have? Look at your periodic table.
4.
4. How many does oxygen have?
6.
6, perfect. And there's 2 of them, so 6 and 2 is 12. So we have to account for 16 valence electrons. Okay, so we have to end up with 16. So put carbon in the center, draw your structure. Let's draw a structure like this, carbon with oxygen around it, and then put all our dots around to make everything have 8. So start with your structure and make everything have 8. There. Okay. Count all the dots. There's 2, 4, 6, and then 2 in the bond, so everything has 8. Everything has 8 around it. So how many valence electrons do we have there? Count all the dots first. So 2, 4, 6, 8, 10, 12, 14, 16. And there's 2 in each line. 18, so we have 20. Does 20 equal 16? Someone should say no,
No.
because it doesn't, right? All right, so something's wrong. We have to lose electrons somehow. So we're going to do what's called a multiple bond. We can make a double bond. So in other words, if we go oxygen, double bond, carbon, single bond. Now put the dots around it. So there's 2, 4, 6, 8 around oxygen, 2, 4, 6, 8 around carbon, 2, 4, 6, 8 around oxygen. Everything has 8. Count your electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. Does that equal 16?
No.
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 Make another double bond. Oxygen, double bond carbon, double bond oxygen. 1, 2, 3, 4, 6, 8. 2, 4, 6, 8 around carbon. 2, 4, 6, 8 around oxygen. Everyone has 8 electrons around it. That'll satisfy the octet rule. And we have 2, 4, 6, 8, 10, 12, 14, 16 electrons. 2 in every line, and then count the extra dots. 16 equals 16. This is the Lewis structure for carbon. It's carbon double bonded to oxygen. Okay. Let's do one more like that. Let's use cyanide, deadly gas. That's what we use in the gas chambers for execution of convicted felons that are sentenced for the death penalty. We use sodium cyanide, and it produces cyanide gas, which replaces oxygen in your red blood cells and causes suffocation. Not a pleasant way to die, by the way. So hydrogen, cyanide. Okay. Hydrogen is how many valence electrons? Look at the periodic table.
1.
1. Carbon has how many?
4,
Nitrogen is how many?
5,
That gives you 10. So let's put everything together. Hydrogen, put carbon in the center. Carbon is usually in the center, and then nitrogen. So draw our lines that connect them, and then make hydrogen have 2, which it does, and then carbon have 8, and nitrogen have 8. And then count. How many electrons are in this compound? Count every dot, and then add 2 for each line. So we've got how many?
14.
14. That doesn't equal 10.
No.
Okay, we got to reduce them. Add a multiple bond. Let's go H. You can't add it to hydrogen because hydrogen can only have 2 electrons. If I put a double bond there, it would have 4. So you can't do that. So let's do double bond here. And then make this have 8. 2, 4, 6, 8. Make this have 8. 2, 4, 6, 8. Now everything has 8. Hydrogen has 2. Count them. How many electrons?
Well,
12. Getting closer. Another bond. So since you can't make a double bond with hydrogen, make a triple bond. Carbon and nitrogen. Carbon has 8. Make 2 here for nitrogen. Now count your electrons.
10.
10, which is perfect. And that's the Lewis structure and the shape of hydrogen cyanide.
I like these.
All right, cool. These are fun. And we'll give you one more little kind of switch up on it. We're gonna add them with a charge. Let's do the nitrate ion. NO3 minus. We're gonna put a charge on this one. This is our polyatomic ion, NO3 minus. Let's draw the Lewis structure for it. There. So nitrogen is how many valence electrons?
5,
5. Oxygen is how many?
6,
6. And there's 3 of them. So 6 times 3 is 18. Now you have a negative charge. Every electron is a negative charge. So 1 negative charge means there's 1 extra electron. So we have, what's that, 24? 18, 19, 24. All right, so you got to count for 24. Remember the negative charge is an extra electron. So we put nitrogen in the center, and we attach 3 oxygens to it. And we put dots to make everything have 8. And then we count them. How many electrons do we have there? Count every dot, and there's 2 in every line. So
$28. 2, 4, 6, 8.
I don't get 28. I get 18, 20, 22, 24. I get 26.
I'm counting the dots as 2, but that's still not making it out. I'm sorry. 1.
That's okay. There's 6 around each oxygen, that's 18. 2 on the nitrogen, that's 20. And then 2 in each line, 22, 24, 26.
Yeah, 26.
All right, perfect. All right, so we make what? Let's make a multiple bond. So oxygen, nitrogen, oxygen, oxygen. And now let's put our dots. Make that have 8. Nitrogen has 8. Make this have 8. And this have 8. Now count our dots. 4, 6. How many we got?
24,
24. 24 matches 24. That's it. There's our Lewis structure. Now, when you do have a charge, we put brackets around it and put our charge on the outside. That counts for our extra electron. Now, these are very stable compounds because these are what's called resonance structures. I could have put my double bond here, or I could have put my double bond here, and it would have been the same thing. So I could have drawn it 3 different ways that gives you extra stability. It was called a resonance structure. Okay, so those are Lewis structures, and they're fun to do. Where else are we? We did the prefixes, ionic and covalent compounds. We distinguish between ionic and covalent compounds. Ionic compounds are charges, covalent compounds are shared bonds. If we dissolve ionic compounds in water, ionic compounds will conduct an electrical current. They're electrolytes. When you drink Gatorade, you have electrolytes. Okay. Now, there's been a couple of cases now where parents have froze Gatorade and given it to their kids during sporting events. That is not a safe practice. In fact, it resulted in a couple of deaths already. If you freeze Gatorade, think about this. Okay. Say your son or daughter pitches a baseball game. They deplete their ions in their body, which was what happens, and especially 29 Palms or Yucca Valley or Palm Springs down the hill, Cathedral City. It's hot. Kids outside play, they sweat, they lose electrolytes. If you freeze Gatorade, or not, and I'm not picking on Gatorade, Powerade, any of the energy drinks, what's going to freeze? The water is going to freeze, not the electrolytes, not your sodium, potassium, and all that other stuff that's in there. The water freezes. So when the water freezes, all you're left with is pure electrolytes. So you're taking a kid who's depleted of electrolytes, and you're going to put their body instantly into shock if you give them frozen Gatorade, because all they're going to be drinking is electrolytes, because the water is going to be ice. The water freezes, and that'll put their body into shock. And if they're depleted of enough electrolytes, it's enough to kill them. We had a case in, like I said, I do forensics. So I serve as an expert witness in several cases. We had a case in New Jersey of people that did that. It's a 13-year-old kid. And he just took a big swig of frozen Gatorade, took all the electrolytes, and instantly put his body into shock. Never recovered from it. So if you like your kids, you can freeze Gatorade and then unthaw it. It can be slushes like that, and that's fine. But if you give them frozen Gatorade and they just get that little bit of the liquid that's still in there, that is not a good thing, because that's all electrolytes. Those are ionic compounds because they dissolve in water to form plus and negative charges. So they conduct electricity. That's what they're called, electrolytes. They conduct electricity. Covalent compounds do not dissolve. Okay, covalent compound, like you mix, and they still mix, like salt and water. Salt electrolyte, you get sodium chloride, Na plus, Cl minus, and water. Okay, if you mix covalent compounds, say you're making alcohol, making vodka. Alcohol is water, and we know how to do the Lewis structure for that, and ethanol, CH3CH2OH. That's ethanol. So let's draw the Lewis structure for ethanol just for fun. Okay, since it's so much fun to do this. All right, we have 2 carbons. So how many carbon has how many electrolytes? How many valence electrons?
4.
4. So we have 2 carbons, that gives us 8. I have 3, 5, 6 hydrogens. How many valence electrons does hydrogen have?
1.
1, and there's 6 of them. And 1 oxygen. Oxygen's how many valence electrons?
6.
6. Total of 20. So we got to count for 20 valence electrons. Now notice how I wrote it out. Now you can write C2, H6O, and that's still ethanol. But we write it out like that in organic chemistry. That's why we write our compounds, because it shows us how the structure is. It says there's carbon with 3 hydrogens attached. And there's another carbon with 2 hydrogens attached. Then there's an oxygen and a hydrogen. Just look in the structure, it's wrote on just as it's written right here. Okay, and then make everything have 8, except for hydrogen, which has 2. All the hydrogens have 2, the carbons have 8, and oxygen has 8. So count our dots, then count 2 for every line. How many do we have?
Or I'm sorry, 20.
Okay, you're gonna worry me again. You have 20. Perfect. And that matches. And that's our Lewis structure for ethanol. So ethanol dissolves with water to form vodka, scotch, bourbon, depending on the concentration of ethanol that you use to mix it with. They're both polar, they dissolve within each other, and those are covalent compounds. Now, methanol is CH3OH. It's only one carbon. So it's carbon, and there's one oxygen. Oh, wait, okay. There's only one carbon in there. Methanol is wood, it's called what's called wood alcohol. Methanol is poisonous. Ethanol is, well, ethanol is poisonous too to a larger extent, but you can drink ethanol, you cannot drink methanol very successfully. Now, during Prohibition in the United States, we could not get ethanol. You ever hear the expression, don't do it or you'll go blind? This is where it came from, okay? When they couldn't get ethanol in the bars, they used methanol. Methanol is toxic. It will affect the optic nerve and you will go blind. So people would drink, they drink methanol to get their buzz, mix it with water, and they make methanol instead of ethanol. They drink until their vision got blurry, then they go to the bathroom and throw it up to keep from going blind. That's what's
That's
happening in
idiotic.
Prohibition. What's that?
So that's idiotic.
That's crazy, huh? That's insane.
Yeah.
But that you always have the expression, don't do that or you go blind. That's where it came from. It was methanol affects the optic nerve and toxic poisoning. So you know you're getting the toxic effects when your eyesight starts to blur, then you go throw it up.
That's
I don't
funny.
want to,
Yeah, that's funny because what you're saying about the Gatorade, I've drank Gatorade frozen so many times when I was in varsity volleyball, and now you got me paranoid on that.
I mean, you can freeze it and let it thaw. Okay? And the big thing we see is in baseball. In baseball, you're out in the sun, and when you're pitching a game, you lose a lot of weight, you lose a lot of water, and those electrolytes can put you in a shock real easily. So yeah, no, never drink frozen Gatorade. Let it thaw back out. You can freeze it and then thaw it, and it's fine. Okay, so it keeps it cold. That's fine. Okay, but don't ever drink it while it's frozen because you're just gonna get you can't put your body very easily into shock from all the electrolytes. All right, so we've done Lewis structures, we've done ionic compounds, how they conduct electricity because they produce ions, and we have one thing to go, and that is acids. Acids are fun. All right, so acids, basically, acids start with an H. And we're getting later to determine pHs and stuff like that. But an acid is basically an H, as hydrogen. It dissolves, comes off as H+. That's how we measure pH. That's what determines the strength of an acid. How much H+ ion is released into solution. And we name an acid. If it's only a single element, like HCl, HI, I didn't know how to draw a line, HF, HBr, we use the word hydro in front of it to signify for them. So hydrochloric acid, hydroionic acid, hydrofluoric acid, there should be a B there, hydrobromic acid. Okay, that's for each individual element. Now, if it's a polyatomic ion, okay, then we use the name of it, like H2SO4. Okay, that's the sulfate ion, the polyatomic ion. So this is sulfuric acid. Sulfuric acid is battery acid. Okay, that's what we have in our car batteries. Nasty stuff. It will burn right through skin, right through clothing, right through skin. Okay. What else did I have on there? HNO3. Again, look at, that's a polyatomic ion. That's the nitrate ion. So this is nitric, N-I-T, nitric acid. So if it's only a single element, we put hydro in front of it. If it's a polyatomic ion, we use that name, and it's ic acid. We change it to IC acid. So sulfate, which is SO4 2-, becomes sulfuric acid. Nitrate becomes nitric acid. Okay. Notice the combination. The sulfate has -2 charge, so we have to have 2 hydrogen to balance it. Remember, we're always balancing our charges. Nitrate is NO3 minus 1. We only have 1 hydrogen to balance that. Okay. And that's how you name different acids. And again, we'll get more into acids in, I think, chapter 7 or 8. We're doing the pHs and everything else. And that is chapter 5. Pretty cool. I think that's it. It goes into the next. Yeah. All right. Any questions on chapter 5? Or any questions on, let's do chapter 5 first. Any concerns with that one? I realize not all have done it all yet, but like I said, what really helps is that one of the students they went through chapter 4 and they had more questions. So the student emailed me, said, these are the questions I have, and I prepared them, and we did them at the beginning of class. And that's how you can get things accomplished. Always, never be afraid to email me. And I can explain it. If you have questions, we can go through it. It works out real easy that way. So don't be afraid if we've already passed it. Like if you got a question from chapter 2 or chapter 3. Chapter 2 had a lot of conversions in it. If you don't understand something, just email it to me. And I promise you, if you have the question, someone else has that question too. Not everybody's just going through this, just reading it like Alice in Wonderland, like a novel. Chemistry has to be read word by word by word. It's very meticulous reading. Okay, and it's a lot of information being presented at one time. And I know that. So I will work with you. And the best way to do it is get your study time. Just if you get hung up on a question, write it down, send it to me. Easiest way to do it. All right, so that being said, any questions on chapter 5? Not on chapter 5, then anything?
Chapter 5 so far now.
Okay. Yeah, you did really well with this chapter.
Yeah, I love this chapter. I didn't like the other ones, but
Any questions on 1 through 4?
Yeah, I have a question on homework number 2.
Okay.
So it just says determine the sum. And it's 9.592 times 10 to the negative 6 power.
9.592 times 10 to the negative 6?
Negative 6, yeah.
Negative 6?
Plus 1.220 times 10 to the negative 4 power.
Okay. You need to put your exponents in the same grouping, okay, to be able to do it. Okay. Easiest way is to just write them out the longhand way. I won't put questions like this on your midterm because it's just a lot of manipulation with math. But to do them, the easiest way is to have a calculator that has sign notation and plug it into a calculator that way. Just put in 9 point. Does your calculator have an EE button?
Let me check. Let me go grab it real quick.
Okay, yeah, as an EE or a caret would be an exponent button. That's the easiest way to do these. Or you can just write them out. 0.1234. Let's see where we're at. 9.9592. And it's negative 6. 1, 2, 3, 4, 5. One more 0. 6. Okay. And the other one is 0. 1, 2, 2, 0. And 1.1234. Okay. Did you make it back?
Yeah, sorry. I don't know what happened to it.
Okay, no problem. This is how you do it. You write them out in decimal form because they have to be able to add apples to apples. So this is 9.5, and the decimal point was at between the 9 and the 5. So I moved it 1, 2, 3, 4, 5, 6 places. Decimal point between the 1 and the 2, I moved it 4 places. 1, 2, 3, 4. And then add these together. 92, 5, 11, 3, 1, 0, 0, 0, 0.0. Okay. we're only good to our least accurate number. So this becomes 0.000. What did I do? 0.000131. And this is greater than 5, so this becomes 6. And then put it back in notation, it becomes 1.316 times 10 to the, and we move this 1, 2, 3, we move this to 1, 2, 3, 4 places. -4. So that'd be the answer. But that's how you do it. You have to, and like I said, I didn't put anything like that on your midterm. It's just time consuming, and students make so many stupid mistakes because it's easy to make a mistake when you have so many zeros you're trying to figure out. And I don't want to make stupid mistakes. I want to test your knowledge of things. So, but that's how you would do it.
On my calculator, I got 1.32 to the 10 to the -4.
Correct, but it rounded it off.
Okay, yeah, that's what okay, so that would be fine too.
Yeah, well, it should be 1.316. You have to be as accurate as your original numbers. But your calculator is set to round it off. So, but that would be okay, yeah.
Okay.
You got to remember your test is going to be multiple choice. So you'll be able to see the number that's closest. Even if your calculator rounds it off, you'll still see the closest correct answer. Make sense?
Yes.
Okay.
I have another question.
Sure, go for it.
Okay, so it's basically the same thing, but instead it's subtracting. So it's 2.204 times 10 to the negative, I'm sorry, times 10 to the 4 power. Yeah.
Okay. Minus.
7.661
Well, that's a funny 7.661
times 10 to the third power.
10 to the third.
Yeah.
Okay. So write it out. So this becomes 1, 2, 3, 4 becomes 2, 2, 0, 4, 0, right? Let's move this place 1, 2, 3, 4. And then minus 7 times 10 to the third. 1, 2, 3. So 7, 6, 6, 1. That becomes 1, 2, 3. Okay? Those are the numbers written out into decimal form from their exponents. So far, so good?
Yeah.
All right. You make me subtract these numbers, huh? 3, that becomes a 10, that becomes 9, that becomes 1, that becomes 10, that becomes 9, that becomes 13. So 7, that was 9, that was 3. That becomes 1, that becomes 11, that becomes 4, that becomes 1. I hope I did that right. Or you could use a calculator for that part. Okay. Now you're only accurate. Well, you're accurate to just before the decimal point. So that's our accurate number. So it becomes 1.4379 because we're good to in front of the decimal point because of this number right here. Or wait a minute, or we get to this one. 2204. We're only good to this point here. Okay. Sorry about that. Let me explain that a little bit differently here. I didn't look up at that right. Okay. So now this is our answer, but now we need the right number of significant figures. So the least accurate number is right here, 2.204. So those were the digits I had. So we're only good to that place. I added the 0 as a holding spot. Okay. I was only good to the hundreds place, one place before the decimal. So we're only good to right there. So this runs out to 143. So let's put in scientific notation. This number becomes, I move this decimal from here to 1, 2, 3, 4. 1.4379 times 10 to the fourth. And we're only good to this place right here. So it becomes 1.438 times 10 to the fourth. Okay. Do you follow what I did, the significant digits?
Yeah,
Okay,
I get that.
okay, and that's what your answer would be.
Thank you.
Sure, no problem. Other questions? Everybody understanding everything. That's good. I know it's a lot to take in. I know it's a lot to do. That's why I encourage you to go through it and just let me have questions, because that's how you learn. By asking me the questions you don't understand. I know it's a lot of stuff to go through. Anything else?
I have more questions.
Sure.
Okay, let me go to them real quick. Okay, so this one just says perform the calculation and record the answer with the correct number of significant figures.
Okay.
So it's 6.5 minus 6.06 divided by 4.76.
Okay. Let's do the top first. 6.5. Let me do this on minus 6.06. And please don't make mistakes here. 6.5 minus 6.06 is equal to 0.44, right? 0.44, and you're only good to one place past the decimal. So this becomes 0.4. Okay, you're only good to that one place past the decimal, least accurate number, divided by 4.76. Okay, so 0.4 divided by 4.76 equals 0.08403361. And you only get to one significant digit. That's all your answer is here, right? So you only get to right there. So it comes out to 0.08 as your answer.
Okay,
That makes sense?
yeah, I don't know why I struggle with these, but yeah, it makes sense.
Okay, no problem. I know the more you do, the better you get at it. Other questions?
So I'm sorry, it's saying that it's wrong.
What's that?
It's saying that it's incorrect.
Okay. What does it say? That's how I would do it. Does it say,
It says, you may find this list of rules for significant figures following subtraction and division help. Do not round your answer until the very end of calculation.
oh, they want to do it. So they want you to do the whole thing, then round at the end?
Yeah,
So you can do it different ways. There's different ways to do it like that. But so you can do 6.5, 0.5. Like I said, this is how I would do it. Minus 6.06 equals 0.44 divided by 4.76. That comes out to 0.09243697. Okay. So at two significant digits, then if I round it down to, I would use that as two significant digits, because this is 3, this would be 2. It would be answer put 0.092 if they did it that way. Well, they rounded it off at the end. But I'll accept, I would accept either way of doing it. That's how I would do it to keep track of my significant digits. When you mix multiplication and division and adding and subtracting, there's different ways to do it. Is that what they were looking for, 0.092?
Yeah.
Okay.
That's it.
That's how they did it. But that doesn't take into account this least significant digit right here. So like I said, I do it the other way, but they can do it that way too. All right, perfect. Other questions? Miles, what's that? Good. Want to do math with us?
I have a question.
Sure.
So it says convert 58.3 meters cubed to liters.
Okay.
Note that 1 milliliter equals 1 centimeter cubed.
Right. That's our magic conversion from measurements to volume. 1 cubic centimeter is the exact same thing as 1 milliliter. All right. So you got to remember you're working with cube numbers, so everything has to be cubed when we're working with it. So you start out with 58.3 cubic meters. And from cubic meters, I can go to cubic centimeters, right? I can have meters cubed and then centimeters cubed. Okay, and instead of writing C, I can write what? What is C equal to in the metric system? 10 to the negative 2. Remember to put parentheses around things because you're cubing both sides. It's a volume. Okay. So the hard part of this was just remember how to set this up. Remember, it's centimeters cubed, and you're putting a 10 to the negative 2, but you're going to cube that 10 to the negative 2. Because everything is cubed, all your measurements. So now you have a cubic centimeter, and that equals a milliliter. And a milliliter is, milli means 10 to the minus 3 liters. So you meters cubed, centimeters cubed, milliliters, and you're left with liters. So it would be 58.3. And on the bottom, you have 10 to the minus 6. You move that up, it becomes 10 to the 6. On the top, you have 10 to the negative 3. So 58.3 times, what's 10 to the 6 times 10 to the negative 3? So 6 minus 3 is 3, which in science notation becomes 5.83 times 10 to the, I moved this place, I made this smaller by 1, make this bigger by 1. Okay. The key to doing these, most students forget, just put parentheses around that 10 to the minus 2. Because remember that has to be cubed. It's a volume measurement. It's 3 separate measurements to make that volume.
Where did you get 10 to the 6?
How do I get 10 to the 6?
Yeah.
Right here, 10 to the negative 2. 10 to the negative 2 raised to the third power, cubed. When you raise
Okay.
exponents, you multiply. When you multiply exponents, you add. When you raise exponents to another power, you multiply. Make sense?
Okay. Yeah, that's the only thing I was confused about.
Right, that's what most students get confused on right there. Anything else? It worked much better today, boy. On Monday, we couldn't get anything to work right. Everything kept cutting out, but at least it's working today. Everything works pretty good.
I have a question.
Sure, go ahead.
Okay, so I have to convert millimeters to meters. So I have 634 millimeters, and I have to convert that to meters. I don't really know how to do that.
You have, say it again, you have 634 millimeters,
Yeah,
and you want to convert that into meters.
right.
Okay, so that's what you're starting with. So 634 millimeters. So again, you don't want to change the number, you just want to change the units. So you have millimeters on the bottom, right?
Yeah,
That we can cancel. Then you have to convert this to meters, and to make this value right here equal to 1, you have to have the same thing on top and bottom. So milli in the metric system means 10 to the negative 3. So instead of millimeters, you write 10 to the minus 3 meters. It's the exact same thing. That way you're multiplying by 1 and not changing your unit, just your value. So you end up with 634 times 10 to the negative 3, which is 0.634 meters.
okay.
Just remember that you're going to have to cancel, top and bottom have to be the same, and then make sure this is equal to 1. If you multiply any number by 1, you don't change the number. You only change the units.